So what we're going to do this week is we're going to experimentally um, test and predict some of the cooling curves. And these are the ones that are going to happen when you have a hot object in a cooler environment, somewhat like we were talking about in the class on Thursday, Wednesday or Thursday. Now, the hot object we're going to use is just going to be hot water. So we're going to have three cups. We're going to have, once again, a cold, a warm, and a hot. So something that's kind of out of a kettle, maybe about 80 centigrade. Something that's warm, warm to the touch, could be hot tap water, somewhere around 40 centigrade, and something that's cold, like a little bit colder than room temperature. So we're going to actually also test the heating curve for that one. What we're going to do is we're going to get the cups of water, put the thermometer. Your lab kit has a thermometer in it. You put the thermometer into it, and then if you use your cell phone video or somehow take a video of the thing, then what we're going to do is we're going to take that video, import it into a software program that was written by a former Cabrillo instructor. So I will guarantee its safety. And it's called Tracker. And so what we're going to do is then have Tracker tell us the temperature at about maybe 15 to 20 different points in time, and we're going to then plot that. Okay, so we're going to plot that and then take a look at what the data is telling us. This will then be compared with what we predicted. What do we think it'll look like? Okay, so let's go take a quick look here at what we've got. So Newton's law of cooling, okay, as I presented it in class, remember, uh, deals with the temperature differences between the cups of water and the environment. So I'll assume, for example, that we have the hot cup of water or something like this, and uh, we've got our thermometer in here. Okay, it's reading whatever it's reading. Maybe it's here, and this is really hot water. So what's going on is there's a heat transfer out of here, and we're going to try and model the temperature as a function of time, both by using uh, a prediction and what we know about Newton's law of cooling, and then we're going to take the data to see what does it really look like and what kind of matching up do we get? Okay. So the temperature difference between water and the environment, the surrounding air, is so you'll need your temperature of your environment. And so you'll need that. We'll call that the temperature of the air. So make sure you take that first and remember that that's what it is. Essentially, what Newton's law of cooling is that the difference in these temperatures changes um, according to the value, right? The rate of change between these two temperatures, the water temperature and the air temperature, the rate of that change is dependent on what that value is. And so whenever you get something like that, it's compounding. It's like a compound interest problem. So this is a an exponential. What it's telling us is that the temperature of the water, okay, so if I measure this temperature right now and I see that it's going to be whatever it is over here, I'm going to say this is a measurement of T. And I'm going to notice that that T is dropping. So this temperature is a function of time. That's for the water, okay? When I measured it at time of zero, when I started the measurements, I'm going to call that zero time, it had a particular value. All right, so T of T, we're going to call, or I should say maybe T of zero. T of zero, we're going to call T naught. And Newton's law tells us that the temperature of the thing itself minus the air temperature is equal to the temperature we started at minus the air temperature times E to the minus T over tau, where tau is a typical time constant, and it's dependent on things like um, what the material, like what kind of convection is happening, what kind of heat transfer rates, what kind of heat transfer coefficient we're having. Nonetheless, and the area of the thing, all this type of stuff. But nonetheless, what we're going to do is we're going to assume this is a constant, and um, we're going to try and measure this. Okay. Okay, so this is basically the equation that we're going to be using. The first thing to do uh, before doing any of the measurements is to make predictions. All right. So let's please predict what's going to happen uh, to the temperature of the hot water, the warm water, and the cold water as functions of time, just graphically. Right. So take a look and see, all right, what do I think's going to happen? Okay, I'm going to have I could do one of two things. I could look at either the temperature difference as a function of time, or I could look at the actual temperature as a function of time. Okay, so you can do either one of those, whichever one you prefer, um, and try to think, okay, well, what is it going to look like when it's hot? What's it going to look like when it's the cold water? What's it going to look like when it's the warm water? Do all three of those on one set of axes, right? So pick whichever one of these you're going to go with and then plot all three of those on there. Okay. Um, Once you have that prediction, then what you're going to do is maybe give a little bit of explanation, right? What's the physics that you are pulling in order to make the prediction of, well, I think the hot water is going to look like this, the cold water is going to look like that. So, okay, so why are you thinking this? All right, so please make sure you do that. And then what we'll do, I've linked into the lab write-up a video on how to use Tracker to take these temperature measurements. So that's linked in the Canvas page. It's called John's video in the lab write-up because it was done by our former lab technician. And he goes through and shows you how to use Tracker and how to take the measurements. Okay. When you have the thermometer, and he shows you all of that. So please, it's only about, I think it's about 7 minutes. So please make sure you watch that on how to use your video and get the data out of it. And then what we're going to do, so let's experimentally what to do taking the data. Um, what we'll do, right? We'll have the warm, and we'll have the cold. And so what I'd like for us to do is to make sure that we get the 15 to 20 data points. We put them into Google or whatever online um or if you want to use Excel on your own computer, that's fine. Send, attach the file in or whatever. However you do that with whatever spreadsheet you're going to use. Um, I'd like you to see if we could measure what the time constant is, right? So the time constant, uh, tau, okay, is basically a measure of, it's like a characteristic time, okay? What I'd like to do is to, uh, what I'd like to do is go up. There we go. What I'd like to do is take a couple of different data measurements and so say I'm going to compare initially how long does it take all three of those waters to change temperature by 15 centigrades or something like that, right? You're going to maybe make a few comparisons with that. And also ask yourself um, to predict how long does it take the water to reach room temperature. So on the graph, since this is a mathematical equation, which is ideal, it doesn't have any time. The time it reach the time to reach uh the equilibration of temperatures is infinity according to the math equation. So we're going to make something a little more practical. So how much time before uh the water reaches room temperature? So what we're going to do is we're going to call that a time of 5 constants. Okay, because by then, if you look at the exponential uh nature of this thing, okay, this thing right here, by the time t has reached 5 of the time constants, right, that means that e to the minus t over tau has become e to the minus 5. And e to the minus 5 is a small number, as it turns out. And if I am remembering, it's something like, I can't remember if it's two or three zeros. It's somewhere, I think it's two zeros, right? Which means that it's 0.7%, right? In other words, you have encompassed what you have left over then encompasses 99.3% of the temperature drop. And for our purposes, that will be fine. Okay. So, um, try and look at what you would predict for that. Okay. What you would predict for that given uh, I'm not saying you have to wait for the water to reach room temperature because hot water reaching room temperature could maybe take a while or not. Depends, right? But nonetheless, uh, take your data points and see if you can find, based on how the curve fits from your spreadsheet, see if you can find uh, what the time is until it reaches room temperature as predicted by your experimental measurements. All right. Let's see. Other than that, I don't think we need to do too much else. I think that we've we've got pretty much what we need. So just making sure we've got the time constants. Okay. They should probably be fairly close in value, but we'll see how they go. This is going to be a much less I don't know if intensive is quite the right word, but it's there's less to do during this lab. It's mostly just the data analysis and how to use the tracker program. Which by the way is very useful. You don't have to use it doesn't have to be many people have used it for other things. It doesn't have to be only um, it doesn't have to be only physics based or only temperature and thermometer based. It could be a lot of different things. It's a very useful video analysis tool. Um, all right, so when you're done with that, um, please go ahead and submit your write-ups and your data, and I'll go for Wednesday because I'm posting a day late here, so I'll give you an extra day on getting that finished up. All right, so hope that goes well for you, and we will talk to you next time.